Over 50 years ago, Americans reached the moon in a race to surpass the Russians. Today, the moon holds a far greater purpose: to serve as the gateway linking Earth to the rest of the solar system. Even SpaceX understands the strategic importance of establishing a permanent lunar outpost, as its primary goal of Mars colonization is dependent on this critical step. Enter Starship, more than just a transport vehicle. Starship itself is set to become the cornerstone of lunar colonization and eventually deep space exploration and interplanetary travel. But how will SpaceX achieve this grand vision? We explore the dawn of Starship Moonbase Alpha. Landing on the moon presents unique challenges due to its harsh environment and lack of atmosphere. Unlike Earth, there is no air to provide aerodynamic braking, and the moon's lower gravity affects descent dynamics. To address these challenges, SpaceX is developing a specialized variant of Starship known as the Human Landing System (HLS), designed specifically for lunar missions. Since the spacecraft isn't intended to remain on the moon as a base but return to Earth, it does not require a thermal protection system for atmospheric re-entry. By eliminating this feature, SpaceX reduces the spacecraft's overall weight, conserving valuable fuel that would otherwise be used for controlled descent and reusability. Another key adaptation is the inclusion of robust landing legs designed to keep Starship stable on the moon's uneven and rocky terrain. And since Starship is much taller than conventional lunar landers, it's designed for stability. Additionally, the HLS variant will feature engines mounted on the ship's hull rather than its base, reducing the amount of lunar dust kicked up during landing, one of the biggest hazards of moon landings. Another crucial modification is the spacecraft's thermal management system. Unlike the stainless steel exterior of regular starships, the lunar Starship will have a white surface to regulate temperature extremes in the lunar environment. This color change plays a vital role in reflecting solar radiation while maintaining stable temperatures for both crew and cargo. Beyond serving as a lander, the specialized Starship will also function as a lunar base. With its massive cargo capacity, it can transport all the essential equipment needed to establish a sustainable presence on the moon in a single flight. Once its primary role as a transport vehicle is complete, the tank section can be repurposed into a habitable living space for astronauts, reducing the need for separate habitat modules. However, just being there won't be enough to build and maintain a lunar base. The key to long-term sustainability will be robotics. While astronauts walking and working in low gravity may be iconic, the reality is that much of the heavy lifting, construction, and resource gathering will be performed by machines. Space suits impose severe movement restrictions on astronauts, making many tasks impractical. Prolonged exposure to lunar dust, known for its highly abrasive nature, can degrade spacesuit materials and compromise their protective capabilities. Even more concerning is the lack of a lunar atmosphere, which leaves astronauts exposed to dangerous cosmic radiation. That's why using robots and autonomous rovers is a necessity. The construction and operation of a lunar base will require near-continuous activity outside the habitat, including excavating large amounts of lunar regolith for infrastructure and resource extraction. These tasks demand physical capabilities that far exceed human limitations in strength, endurance, stability, and operational duration. Robots can work tirelessly in extreme conditions without the need for rest, making them ideal for lunar development. One important design consideration for lunar robotics is power efficiency. Unlike on Earth, where heavy-duty construction equipment relies on large internal combustion engines, lunar excavation will need to be approached differently. Studies suggest that high-powered vehicles greater than 10 horsepower will not be necessary for an early lunar base that produces around 100 tons of liquid oxygen per year. Instead of using high-speed, heavy-duty equipment, robotic systems on the moon will employ slow, steady movements and precise excavation techniques to collect and transport regolith. This minimizes dust disturbances while conserving energy. Since solar power availability fluctuates during the 2-week-long lunar night, power systems for these machines must be highly efficient and adaptable. Meanwhile, astronauts will focus on tasks that require decision-making, complex problem-solving, and scientific exploration. Their responsibilities will include testing and qualifying new technologies, troubleshooting and repairing intricate equipment, and pushing the limits of robotic operations. They'll also play a critical role in scientific investigation, studying the lunar environment and potential resources for future use. A successful lunar base will be a collaborative effort between humans and machines, with each contributing their strengths to the mission. Robots will handle the bulk of the physical labor, while astronauts will oversee operations, conduct research, and ensure that systems function optimally. SpaceX's vision for a permanent lunar presence, powered by Starship and advanced robotics, represents a bold step toward humanity's future beyond Earth. As we prepare for this next giant leap, the development of specialized spacecraft, autonomous machinery, and efficient power systems will be key to unlocking a new era of space exploration and settlement. Now that we've covered the necessary preparations, it's time to establish a moon base. The chosen location for the moon base is on the rim of Shackleton Crater at coordinates 89.78 degrees south by 155.73 degrees west. This site is ideal for several reasons. It receives ample sunlight, ensuring a reliable energy supply. It's close to permanently shadowed regions, making it suitable for water extraction, and it offers a flat, spacious area large enough for a ship to land safely and maintain stability once positioned horizontally. Although we have a landing site, we will not proceed directly to the moon. Instead, we will first send an unmanned Starship carrying essential equipment and resources to establish the base and sustain the next crew for an extended period. This phased approach allows us to lay the groundwork in advance, enhancing crew safety if any issues arise with the unmanned mission. If the first phase proceeds smoothly, the crewed ship will land shortly thereafter, at a location not too close to the initial landing site to avoid lunar dust interference. Once landed, unloading, deploying, connecting, and activating solar panels, power reactors, and radiators will take precedence. We can begin transforming Starship HLS into Moonbase Alpha as soon as initial system checks and documentation are completed. The first step involves laying down the HLS so that it rests horizontally. One proposed method utilizes a cable system, which includes a hinge at the vehicle's base, cables positioned midway, and a scissor lift that moves along the vehicle, providing structural support. The lay me down gently process begins by folding the lander leg in the predefined tilting direction. The elevator system will gradually deploy the cables, increasing the tilt angle. At a critical tilt angle, the tension in the cables transfers a load to the scissor lift, which ascends along the vehicle's body. Upon reaching the nose, the lift folds, allowing the vehicle to settle onto pre-piled BMS, ballasted modular structures, or embankments. With the vehicle in position, methane will be fully drained and stored in designated bladders. Any remaining fuel in the tanks will be vented to eliminate fire risks during interior modifications. The nitrogen in the payload area will be supplemented with oxygen extracted from the tanks, while the oxygen tank will be replenished with nitrogen to achieve proper air and pressure balance. Converting Starship HLS's fuel tanks into habitable volumes will significantly increase the base's livable space, which will be about 2.5 times more spacious than the ISS. All internal walls will be lined with insulation and radiation shielding, enhancing safety for the construction crew. 2 additional floors will be installed to create 3 living levels, each nearly 3 meters high. The interior will be equipped with private and communal living quarters, including sleeping pods, kitchens, and a lounge area. Scientific research spaces will include a laboratory for soil-free plant growth, ensuring stable food supplies for the crew. The final stage involves installing communication, electrical, ventilation, and water distribution systems. To protect against radiation and meteorite impacts, the entire base will be covered with a 5-meter-thick layer of lunar regolith. SpaceX's conceptual renderings indicate ambitions beyond a single moon base. They envision an entire lunar settlement or colony. Therefore, the Starship moon base configuration must be scalable. Expansions can be achieved by linking additional horizontal starships via a dedicated node at the vehicle's top or through airlock corridors. The primary challenge is transporting these extra starships to the same location, as they cannot land too close together due to, dust. A transport rover system could solve this challenge, distributing the weight of the new Starship for relocation and docking. Astrolab Flex rover is a promising candidate for this task, designed for NASA's Artemis mission. The Flex rover is a highly adaptable vehicle capable of carrying 2 astronauts in full space suits. It also features a robotic arm for advanced scientific research and supports robotic cargo logistics. The Flex rover will play a crucial role in future lunar missions. It will launch aboard a SpaceX Starship, with a smaller prototype set for a lunar mission later this year to test core systems, including batteries, tires, avionics, sensors, and software. I can't wait for this mission. I'm going to flip out. For long-term lunar habitation, we must produce our own food and water. Japan is already making progress in this area. Last month, SpaceX launched 2 lunar landers into orbit, one of which was Japanese. This lander carried an innovative payload featuring a water electrolyzer experiment and an algae-based food production module.